All right, shall we start? Okay, before we start, actually, we have some announcement here. Actually, CA1 will be the whole the week after the recess week. So that is March 15th. The time is 3:30. Actually, the same time as the normal class, and in this room, okay, 86. Okay. So that week we will have another lecture, and we also have another tutorial. Okay, because that week I will fly to the USA for the conference. Okay, so we do have the CA1 at that time. Okay, the CA1 will cover the lecture 1 to 6. Okay, as shown here, and then tutorial the 1 to 4. Okay. So we only have the 4 structure questions for the CA1. Okay. So if you have any comments or any suggestion, or if you don't know, just let me know. Okay, you can talk to me. Okay, so last week we talked about actually the PMC, MMC. I just gave a summary about this part. Okay, for the PMC, actually we have several methods. Actually, all these methods is based on what kind of the polymer matrix we use. Okay, because the polymer matrix we have 2 types. One is the Summa setting, another Summa plastica. For the Summa setting, we use the Hanna lab or the SPLAB. Okay, but we also have other methods. We are going not talk about it. If you are interested, you can find me. Of course, in this class, we only talk about the Hanna lab and the SPLAB, and then in the final exam, we only cover these 2 parts. Okay, for the Summa setting, for the Summa plastica, we have the 4 methods, but in this class, we only talk about the 3 methods. One is film stacking, the Summa plastica type laying, and also the commingled fibers. Okay. Of course, we also talk about the collision model process. Okay, collision model process, we only talk about actually the complexion modeling. Complexion modeling actually have 2 types. One is actually the positive pressure, right? Another actually is the negative pressure. So that means we use webcam to do processing. So these 2 methods you should go back to look at it if you don't know. Okay. And besides that, we also talk about for the Summa setting polymer, we definitely need to do cooling. Okay, for the cooling, actually, there's 3 factors we have about the cooling. One is actually the time, temperature, and also the pressure. Okay. Besides that, we also talk about the finishing method. For the finishing method, actually, we talk about the cutting, right? And also we talk about the trimming and then deflashing. Besides that, we also talk about the loading method and the polishing method and the painting method. And more importantly, you guys should be careful is actually the defect, because during processing, actually some of the condition you didn't pay attention, and then in this case, you may introduce a lot of defect in the composite. For example, incorrect cooling conditions. This will including the temperature and also including actually the pressure. For example, temperature too high, and you may have problem, or temperature is too low, you may also have problem, and also according to the pressure. Besides that, actually the fiber, okay, if you use a broken fiber, and because the fiber is broken, of course you will introduce a lot of defect inside, right? And also misalignment, as I mentioned before. If we use longer fiber, all this direction, right? If it's a fiber, one layer and another layer of fiber have some actually the angle, division angle. If angle let's say 15 degrees, and then this reinforcement will be reduced about 50%. You should be really careful for that. Besides that, actually all the fiber surface should be very clean, right? If we have impurity on the surface of the fiber, you have problem. One thing is actually impurity, you will introduce impurity inside. Another thing is impurity will affect the interaction between matrix and also the fibers, right? So you should be careful. And of course, we talk about the CTE. CTE actually is a coefficient of the thermal expansion. So that means during process, you maybe use a high temperature. When you cool down, and actually in the fiber and the matrix is two different materials. So in this case, their coefficient may be different. And then when you cool down very fast, you may introduce actually the stress inside. And this stress later on actually is a weak part, okay. Besides that, actually, of course, talk about the water. You may introduce the water inside. You should be careful for that. Besides that, we also talk about the MMC is metal matrix composite. Metal matrix composite, and then we only require several methods. For example, for the liquid processing, we have three methods. For example, one is actually the casting or the liquid infiltration, and also come to squeeze casting, or this will cause another pressure infiltration. And infiltration is very important actually later on for the CMC and also the carbon composite materials, and we also talk about the infiltration, okay. And also the spray forming, this method we talk about special actually is atomize. So what is atomize? You should go back to look at it, right? And also we talk about solid processing. Solid processing, we talk about the dissolution bonding. Besides that, actually for the physical processing, for example, we talk about the PVD, a lot of the PVD method, and also we talk about the electroplating and also CVD method, right? All these methods, actually some of the methods has already been taught to you guys actually in the year 1 or maybe year 2. So some methods should be easier. So actually I just summarize all the things here, okay. So now we talk about the CMC. CMC actually is a ceramic matrix composite, okay. So this material actually is very important, okay. One thing, because all these material can go very high temperature. Normally this CMC actually have two types of materials. One is actually oxide, another is non-oxide. Oxide, as we know that oxide can go very high temperature, okay. So for the CMC actually, we have a lot of these second phase. For example, we can continue fibers. We can use actually the fiber, we cut it at a small piece, or we can use actually viscous, we can use particles, and also can use plates to enhance the properties, okay. So typical actually we have several actually the matrix. Typical is metal oxide, which is shown here. Let's say aluminum oxide, zirconium oxide, or silicon oxide, right? Of course, for the non-oxide, we can the silicon carbide, right? Boron carbide, titanium carbide, or the silicon nitride. Especially for the silicon carbide or the silicon nitride, these two materials is very, very important. For example, silicon nitride actually is a very good packaging material for all the semiconducting conductor industry. Whatever their device, right? If you before actually the sale to you, they need to use a silicon nitride to cover it. Especially like the Singapore, actually the moisture is very high. If we didn't use this silicon nitride to cover it, actually the moisture can easily to get inside to damage your device, and your device actually cannot use for longer time. Okay, so this actually silicon nitride and the silicon carbide is very important packaging materials. Okay. So of course, different materials, they have different application, right? For here, for this one, actually normally oxide can use as the heat resistant materials, right? So that means this material actually is a heat insulate. So that's means a lot of the actually furnace oven, they use this metal oxide. Look, right? So inside the temperature can go very high temperature, let's say 1000 degrees. If you do FYP and then if you use the furnace or use the oven, you should really know that actually you can put your stuff in the furnace and then of oven you heat up a very high temperature, let's say 700 degrees and 800 degrees, and then we can keep that temperature. Why we can keep it that? Because we use a lot of the composite actually is oxide, right? Besides actually all these material can be used cutting actually the tools and also have a lot of structure applications. Okay, for the non-oxide materials actually we also have a lot of application. Especially they can use abrasive materials. So what do you mean abrasive materials? So that means the surface we coating with this material. This material, the surface is not that easy to the scratching, right? Typical material, if you do the scratching, actually you will see a lot of actually the glove on the surface. The material surface will become actually the rough. But use this material coating, and then the surface will become very smooth. Okay, so this actually have a lot of the applications in our daily life. So typically, actually, the also have shows application. For example, they use military and then aerospace, right? And then a lot of the applications. Okay, and also actually, for the CMC material, actually now is a very hot topic is what lithium battery. Lithium battery actually inside use whatever use a cathode or anode, maybe cathode. Okay, they use a lot of the oxide, right? Or the let's say lithium iron phosphate. That one is actually the cathode materials, right? So actually this has big application in the energy conversion materials, right? Of course, actually for energy conversion materials, for example, you want to travel this actually the let's say solar cell energy to some the electricity, or to other energies, or maybe solar cell energy to the chemical energy. All these material, for example, we can use a photocatalyst, right? So actually all these material have big applications in energy conversion. Okay. What happened? Okay, so for the processing method actually for the CMC method is slightly different from the metal oxide because of different from the MMC, because the metal, most of the cases we can heat up at some certain temperature, metal has some melting point, become melt. But for CMC, the big problem is most actually the ceramic materials, they have no melting point, or the melting point is very, very high. So we cannot use actually the liquid processing. Most of the case we use actually is cold placing or hot placing. This actually is easy to understand. So for example, we can powder and then you mix them together. You just give the high pressure and all this will become disc. So if you do the FYP, for example, if you do FTIR, we can sort and mix your sample. You mix them, grind them together, and then you put some of the dye, you give the pressure, and then you can give transparency sort window. Right, so that one you can do the FTIR, right? So if you know how to do FTIR, and you should be able to know what's the cold placing, right? Besides that, we also talk about hot placing. Of course, here liquid infiltration is very important, right? In the MMC part, and we may talk about the squeezing infiltration. Now we will talk about liquid infiltration, and also for the carbon composite, we also talk about the infiltration. All the infiltration, what do? We need to use actually the preform. Okay, so that's the preform is very important. Why I emphasize in MMC and also in the tutorial, we will talk about the preform. Preform is very important. Of course, this guy we're not going to talk about it, but we do talk about actually the CVI, which is called the chemical vapor impregnation. This method and also solid gel method, we may talk about actually in tutorial. But we are going to talk about more about this solid gel processing. Okay, for cold placing and then plus settling, this is very simple. For example, we have the particle. Okay, you grind it, and then with your particle, with your second phase, you grind them together, and actually this is funnel, right? And then you put a particle, you fill in. When you fill in, and then you take the actually funnel away, and then we have another dye, you put it in, and then you give the pressure. You give the pressure, and all this actually the material actually will be stick pressure, and then becomes disc, right? And all the material will be stick together, right? So it really depends on actually the amount. So this maybe become transparent, right? If you do the FTIR, if you use a salt, there's a KBr, that means potassium bromide, and then if you give a small amount, it definitely can make actually very transparent. Actually, the film. For this one, for our case, actually, when you make this material, it's not enough. You make this composite, and then you should do the settling. So what the settling, that means you need to heat treatment. So you get this disc, right? You get the disc out, and then you need to put the furnace, heat up some certain temperature, let it active maybe for the 3 to 4 hours, and then this material will become much better, right? Normally, when we do it, actually, we may put some binder. This binder actually is organic species. Organic species, we have problem is what? After you make it, and then you have to heat treatment to remove organic binder, and then this material composite will become shrinking. If it's shrinking, of course, sometimes it may form the crack inside, right? So this may have some problem. So you should be really careful to control this binder amount. Some people may be asking me if it's possible for us don't put any binder inside. If we didn't put any binder inside, actually, if we give the pressure, actually, all the material cannot, connect together very well. So bonding actually is very important. Okay, this is one thing. Another thing, we also talk about CTE. CTE, what that means? Because when you make this, the composite, the disc, right? You make it, and then you put it in the furnace, you heat up some certain temperature. When you heat it up, and what will happen? Because you have two different materials inside. You have matrix, and also you have the second phase. These two different materials actually thermal expansion is different. So that means called the CTE is different. So if you cool down very fast, you may introduce actually the pressure inside, the stress inside. This stress, we don't want it. Later on, if you use this material, and then this stress will be the weaker part. That means your material failure will from that part, okay? So this actually is very important. Another thing, of course, this one which has make disc, but in the industry, people can make this mix with the polymer, actually ceramic powder. They mix them together, they can make the tap, actually this tap, okay. So this, actually they do have a big application, okay. So another thing actually that we talk about is actually the weaker interaction. This is actually also very important. For example, if you do the layer by layer, okay. If you do the layer by layer, and then you put all the things together, if the interaction is very weak, and then two layers maybe can be easy to peel off, okay. Another thing, if you the second phase, and then your matrix mix them together, if interaction is very weak, and then you can imagine actually that part later on, the weak part should be between your particle, second phase, and the matrix, that part. That's actually maybe from the crack, okay. So you should be really careful for that. Okay, hot placing actually is much easier. It's just one step, because for the cold placing plus settling, actually we have 2 steps. So we can put all the two steps together. One step is hot placing. But hot placing this equipment is more expensive. Okay, so that means when in industry, you can do the hot placing, but this price compared to the 2 steps, you may be cost more. But sometimes you maybe save the manpower. You need to compare you save manpower, this cost compared to the one step is this one, which cost actually is out of way. You need to compare which one is big and which is small, and then you decide 1 step or 2 step. Right, this is one thing. Another thing, you should be really careful for that. Actually, normally for the hot placing, this pressure is much smaller compared to the cold placing. Okay, this is really the material will determine it cannot go very high pressure. Okay, even we can go very high temperature, but the pressure probably cannot go very high. This is one thing. Another thing, since you do the hot placing, so that means inside that we should normally actually should be the vacuum it, or we should put the inert gas inside. Otherwise, in the high temperature, if you have oxygen inside, maybe your material will be easy to oxidize. Okay, this one you should really careful for that. Okay. So actually the typical, this actually for the oxide is okay. For the non-oxide, I have big problem. Actually, typically, for example, if you try to do the thermoelectric materials, if we use calcinite, most cases we have problem. Actually, we cannot use actually the ceramic. Most cases we use carbon, because calcinite in high temperature easy to react with metal oxide. So in that case, if you want to thermoelectric materials, especially for the calcinite system, normally this dye we use actually is carbon. It cannot go very high. Also the temperature cannot go very high. Okay, normally temperature maybe 800, something like that. If it's too high, still have problem. Okay, so for the thermoelectric materials, when we choose, you should really, really careful. Okay. Anyway, actually, this hot plating should be actually the easy method, one step compared to the previous cold plating. Okay. So now we talk about the liquid infiltration. Liquid infiltration, this method, infiltration method, actually we did talk about in the MMC part. First things, what we do, we should have this preform. How to make the preform? We have two ways. If you don't know, you should go back to look at it. So normally we have preform, and then we hit a very high temperature. Another thing on the top, we have this matrix material. Matrix material, of course, you need to heat up a very high temperature, and then all this matrix material will become liquid. However, this material actually very viscous, as I mentioned before, like the metal matrix, same thing. Very viscous, so in this case, you should use pressure to push in. Okay, so use pressure and push in, and then you can get it inside. Of course, we need to heat up. This temperature should be the same temperature, right? If the temperature too low, what will happen? If the temperature too low, and then when you push in, and then all this liquid will become solidified, and then you have problem to fill here and to fill here, right? Another thing, because this material is very viscous, you may have some problem to fill here, right? Because very viscous. Okay, so during the practical application, you should really careful about this corner part. Okay, of course, actually, advantage is a very obvious, which is shown here, but we do have disadvantage. Disadvantage, we have several. The first things, all the things become liquid, and actually you heat up a very high temperature. Okay, in very high temperature, some actually unwanted reaction or unnecessary reaction happens. So this one, when we design, we don't want this reaction. However, when the temperature reaches some certain temperature, this reaction may happen. If it happens, and then you will introduce impurity inside. Okay, so this, you should be really careful for that. Actually, one thing, the temperature. Another thing, as I mentioned before, is this actually the material become liquid. We call it liquid, but this liquid actually is very viscous. So that means you may have problem to fill all this space. Some space it cannot fill in. Okay, so that's you may have problem. Okay, the third thing actually also we need to think about the thermal expansion, right? Obviously, this second phase and also your matrix probably is two different material. If it's two different material, in this case, when you cool down, of course, the CT is different. You may introduce stress inside. Okay. So typical, I can give one example. For example, we want to make the silicon carbide or the silicon nitride. How to make it? Right. First things, of course, we need to make the preform. This preform, okay, we can use the positive pressure or use the negative pressure. We make the preform first. Right. This preform, we can use the silicon carbide particle or fiber, or use the silicon nitride fiber. Right. Again, go back how to make the silicon carbide the fibers, or how to make the silicon nitride fibers. Right. How to make it. Right. This one we'll go back to. The spin. Right. So that means the silicon carbide. Actually, we have three methods to make it. Okay. If you don't know, you should go back to look at it. Right. And then we make the preform. When you make the preform, the second stage actually you use the melting materials with the precursor. for the silicon carbide. Okay, you melt it. Actually, this precursor can be the small molecule or it can become polymer. You melt it, and then the temperature normally 780 K. Here, right, we use argon and nitrogen. Why? Because all organic material in such a temperature, if you use oxygen or air, this guy easy to oxidize, right? So in this case, you give the pressure and then you squeeze in, right? You squeeze in, but do remember that actually all this actually is organic precursor. So that means we still have the organic species on the surface. So in this case, what do? We need to put autoclave, heat them a certain temperature, paralyze this. So that means all organic species will be decomposed and then eventually will become silicon carbide or the silicon nitride. However, during we do the paralysis, what will happen? You will lose some small molecule. When you lose a small molecule, what will happen? You will introduce some void inside, right? This void you need to go back and then to repeat it. Why we want to repeat this? Because that's a void we need to fill in again. Use the material. You need to go back to here, fill your liquid inside in again, and then repeat this procedure, or to 2 to 5 again, to fill actually the holes. Because when you, the heat of this temperature, material decompose will leave some hole there. This hole you need to fill it, okay? And then you repeat maybe 3 to 4 times, and then you will get your material. After you get a material, of course, you need to heat up some very high temperature to do annealing. Later, your matrix and then your second phase have the bonding, and then they can connect very well. So you will get your materials, right? Okay, so that's actually called liquid infiltration. Another actually is a CVI. CVI actually is a chemical vapor actually the impregnation. So in this case, actually, we use a small molecule, which in this case, we don't use actually liquid. Instead, actually, we use gas because small molecule, you hit some certain temperature, this guy easy to become gas. When it becomes gas, actually, you fill gas in, and then this temperature should be very, very high. So when this small molecule get in, and then in high temperature, what will happen? This guy will decompose, right? And this guy decompose, and then this actually is a preform, fiber preform. You have a lot of polars, small molecule get inside, and then decompose, and then will become the silicon carbide or silicon nitride, and you can fill in. Okay, so this should be easy. Typical, actually, this method we have already touched it actually when how to make the silicon carbide, right? So how to make the silicon carbide fiber, we have already touched it, right? So we use the same material, we fill in, and this guy will decompose, will become silicon carbide. Okay. So typical actually SEM image is like here, right? We take the material and then we look at SEM image. You look at here. This is our fiber, because each fiber will have the polars here, and these polars will fill by silicon carbide, right? Filling by the silicon carbide, right? So this actually is gluing the silicon carbide inside. Okay. So one thing typical when you look at this part, you may have some problem will show up. What the problem will show up? So that means when we fill our gas in, and then gas decompose, and then getting decomposed, and then all these channel maybe have already been filled. Okay, when all these channels have already been filled, you have problem to fill here, right? Because gas inside goes to here and maybe came to here, and here. After you finish it, maybe this part and this part it cannot be filled. The reason is when gas get in here and the gas decompose and fill the channel, fill the channel, and then after you fill here, all the channel has already been filled, and then gas may have big problem to reach this part, right? So this should be easy to understand, right? So in this, how to solve this problem? And then we have another way. So that means we fill the top first, right? We have this our the preform, and this top actually in the furnace temperature is very high. When gas get in, and then the top will decompose and fill top first, and then we slightly put this inside and then decompose, inside decompose. So in this case, we can fill actually this part very well compared to this traditional method, right? Okay, so now we talk about the solar gel processing. Now we have talk about several methods. Like we talk about the cold placing plus seedling. We talk about the hot placing. Now we talk about the liquid infiltration, right? And we talk about the CVI. Right? Now we talk about the solar gel processing. Solar gel processing is something like this. For example, when we do the hot placing, whatever we do the cold placing, actually the matrix and then your second phase, the particle, you mix them together. When you use mechanical mixing matrix and then your second phase cannot mix very well. So in order to let your second phase deposit matrix evenly, very well, and we're starting from actually from molecule. Okay, we have molecule, for example, we have this organic oxide of the molecules. This molecule actually it dissolves some organic solvent, dry solvent. Okay, it dissolving. Then when you add a small amount of water, this guy will decompose, right? You add the water and it decomposes will form the metal hydroxide. However, metal hydroxide normally is not very stable. So in this case, this guy can lose water from the metal oxide. So from solution to the soil, this stage it really depends on what kind of the water you added in. If you add a very small amount of water, and then this will deposit in the solution, and here will become soil. In the solution, you will see the particle. The particle size is less than 100 nanometer. So you form the nanoparticle. And then when you look at the solution, all the solution actually is the clear solution. But you take the solution and then you put it in the SEM, means Gulick, and then you look at SEM, you can see the particle. If we added more water and then all these actually oxide of the wedge actually were connected with another wedge group and lose the water and then we're connected together. If they're connected together and all the solvent will be trapped inside and then will become wet gel. So this should be easy to understand. Actually, in our daily life, for example, you have some soup, whatever, the chicken soup or the fish soup, you put in the refrigerator. Right? If we put a refrigerator and all the things will be trapped inside. The same thing as we talk about is this called the wet gel. And that one also the wet gel. Or you buy some the jelly, right? That one also the wet gel. Okay. From wet gel to dry gel, so that means you use a vacuum, you heat it up, and then you lose organic solvent, right? And then it will become dry gel. Okay, don't remember that from wet gel to the dry gel, actually the gel will be shrinking, and will maybe form crack, right? And then from the dry gel, okay, so in this case, we can use the hot plating, or you can use the cold plating, and then you can form this, the composite, whatever you want to make it, okay. So typical is something like this, okay. So we have this organic species, and then you added water in, and then we form the soil. So that means metal oxide will decompose. Metal organic precursor will decompose, will form this metal oxide particle in the solution. All the particle actually is individual. Okay, the particle size is less than 100 nanometer. In SEM, you can see the particle size. However, if you add more water, and then all particles will be connected together. All the liquid will be trapped inside. From here to here, actually, you just heat it up or you vacuum it, okay, and then you can become this solid. From here to here, actually, is you let the gel stay for a long time, and then all these bonding will be connected together, and all the solvent will be trapped inside, okay, and then they form the framework. From here to here, actually, from dry gel, actually, you just to remove solvent, and it becomes dry gel. When it becomes dry gel, actually, in this material, you will have a lot of polymers inside, right? And then later on, we can use the hot placing. Okay, so one thing is actually how to select the materials, how to select the material materials, and then we have the four, the condition here. One is actually in the high chill yield. This one, so that means we have this starting material, you put it to water, add the water inside, and all this matrix should be completely to become converted to that metal oxide. Okay, so this actually yield should be very, very high. Another thing, low shrinkage. Low shrinkage, so that means during processing, for example, if you remove this solvent, and then the shrinkage should be very small. Okay, And also, these guys should obviously, or whatever means the material should have good mechanical property. Of course, it should be easy for application. Okay, so we have a lot of advantages with shown here. So this one I don't need to to repeat it. Actually, this should be easy to understand. For example, all these processing can do the room temperature. When you mix them together, you don't need to actually mechanical the mixing, right? And then all this bottom up, so all this material the deposit in the matrix should be evenly, right? So this actually should be more easy homogeneous, and then right, and then we can use the multi-phase actually the matrix. Okay. But they do have this disadvantage. One is actually the shrinkage. So this you cannot avoid it. Whatever you remove solvent and all the material will be shrink. So that's actually easy to understand. And also actually have some the crack inside, right? Because when you remove solvent, you will have polyps inside. So this will form actually the crackers. Okay. Okay, so this is this part for the the CMC. Look, let's give a summary about the CMC. So for the CMC method actually processing, we have the cold placing, we have hot placing, we have the liquid infiltration, and we have CVI, and also we have this actually solid gel. So we have 5 methods, right? So you guys should go back actually to look at it. Okay, so now we talk about the carbon composite. Okay. Carbon composite material actually is very important. Actually, this material, when we talk about processing, you can see actually carbon composite processing is very, very difficult. So that's why this material is very expensive, and this material only can be used some special application. Okay. So typical why people use carbon composite. Okay. So this we have a lot of the advantage here. For example, carbon is very light, right, and also the high strength. Typically, actually, the temperature can go, 3,000. Normally, for the metal, 1,000 or below, they will become melt, right? Some people maybe say that, okay, we can use the ceramic. Ceramic, actually, the strength is not that high. Right? Also, ceramic actually is very heavy, okay? So, but carbon itself, big problem is what? When temperature more than 400 degrees, it's easy to oxidize. So actually, that means we need to do protection. How to do protection? Actually, in tutorial question, we have already talked about 1 method, 4 steps, right? If you don't know, you should go back to look at it. Okay. So carbon materials, they have a lot of advantage. For example, the first one is actually is the melting point. Carbon actually never become melt. Okay. So, but for the normally for the metal actually, normally for example metal normally temperature actually is more than the 1,000 degrees. Normally they will become melt. So that's why, for example, for all the airplane, the black they use actually is a carbon-based material instead of actually the rubber or instead of the metal, right? So the carbon actually this material can be used for the airplane tires, right? So this is one thing. Another thing we should really care for actually is what? Is actually for the superconductant. Okay, you should remember that actually graphite, actually this material is anisotropic. Why do you mean anisotropic? Because graphite actually, if you do the the FYP do the graphene stuff, actually graphene is from the graphite. When you have graphite, it oxidizes. You can make the graphene. Okay, so from this one, you can immediately know that actually graphite actually be the layer compound. So that means graphite, we have layer and then all the layer we stacking together. Layer between layer and layer actually the interaction is pi stacking is very weak. But in layer actually is carbon connected together is much stronger. Later on we are going to talk about it. So in this case, all the graphite material is anisotropic material. So that means, for example, we talk about the heat content, thermal conductivity. Okay, in plane, all these carbon-carbon connected together, actually in plant, this heat flow is very high. It's 21.3, right? But a vertical, this direction is only 0.6. This is about maybe 35 times different, right? So this, because actually in plant, they have the chemical bonding connect together, but vertical the plant actually is pi stacking, okay? So this, from this data tell us actually this material is anisotropic materials, okay? Another thing is about the heating. This one actually in our daily life, for example, if you do the roasting, right? You have party, have barbecue, right? And then if we have, for example, if we have longer carbon, materials, one end, it catches the fire, you have already get the fire, but another end is still use the hand to touch it. Why? Because heat cannot easy to transport through this actually the vertical direction. Same thing is here, okay? We have this graphite, okay? We use a laser beam to heat up in the middle. The middle temperature can go very high, 1200. However, you look at the top and look at the bottom, the temperature is still 20 degrees, right? So that means along this, actually the vertical, actually this direction, this heat transport is not that high, okay? But in plant, the heat transport is very, very fast, okay? So this actually, for the high thermal conductivity, it really depends on directions, okay? So another thing, in class, actually, whatever, when starting this class, when I talk about carbon-based material, I always say that carbon-based material actually thermal expansion is 0. So this, when we use carbon-based material, we don't think about actually the thermal expansion. Here, actually, I give some data here, right? Okay, when look at here, whatever in the room temperature is 2000 degrees, actually this thermal expansion is almost 0. But you look at this copper, right? Copper, when temperature increases, actually this copper thermal expansion data is about 16. But for the diamond, actually one of the carbon material is 1.1. This is actually already about 16 times different, right? So from here, we definitely know that actually carbon-based material, whatever from room temperature to the high temperature, you don't think about actually the thermal expansion. But for the metals, you really take care of actually the thermal expansion, okay? Besides that, actually for the heat capacity, okay, this heat capacity actually, this one is very, very important, okay? So you look at here, okay, these are the graphite and this is titanium and this is copper and this is temperature, right? So from here, you look at here, in the same temperature, what will happen? The graphite actually the heat energy input, for example, let's say this temperature, you can look at here. This input is much higher. So that means this guy can take more energy compared to this copper and compared to this titanium. So this material can be used as a heat sink, okay? So easy to remove the heat. So this why also, for example, why we want to use this material for this airplane, the tire, because when you airplane touch down, generate a lot of heat. This heat can easy to remove away by these carbon-based materials. If you use metal, okay, metal temperature cannot remove heat that fast. The temperature will be increased a lot, and metal maybe will become melt, okay. Okay, so another thing that we talk about actually is for this low activity. Low reactivity is really dependent on the room temperature. For example, we have this a piece of the coal. If you want to this guy to catch the fire in the air, it's not that easy, right? So I don't know if you have experience or not, but I do have experience. When I was young, actually, we use a lot of this coal. Now, actually, when we do cooking, we use gas, right? It's not use coal. But in my time, we use a lot of coals, right? We buy from the shop, and then if we didn't pay attention, and the next day maybe this coal have already that means the no fire. So that means you need to ignite again. How to it? Actually, we use a lot of the newspaper, and then we put it to the oven and then put the coal on the newspaper and then ignite it. But this one will take about at least 30 minutes to catch the fire, right? So that's actually is a big problem. But for this one, so that tell us, when things tell us actually in the room temperature, or maybe in some certain temperature, let's say below the 400, if you want to make this coal to catch the fire, it's not that easy. Okay, from here, it's not that easy to ignite. Okay. Okay, maybe we take the 10 minutes rest and then we'll start. Okay. Okay, we'll start. Okay. Okay, before I start, I just someone came here later, and then I just repeated this announcement again. So the 1 week after the research week, we will have the CA1. The CA1 will cover the lecture 1 to lecture 6, and also will cover the tutorial 1 to tutorial 4. Okay, and then the question actually we have 4 structured questions. Okay, and then the time is the 3:30 p.m. to the 4:30 p.m. Actually, the 1 hour in this room. Okay, so that means in the March 15th. Okay. Okay, so now we talk about actually the carbon material. Carbon material actually is very, very important. Recently, actually, if you read some of the news about this graphene, okay, graphene actually, people have already claimed that they make the lithium battery use the graphene, right, and the high charging, the faster charging, and also actually the capacity can go very high, and then some company claim that they have already can be used, but at the same time, also some group, also some very famous professors, they write a lot of the comments say that okay, graphene probably actually is not as excellent as we reported for the lithium battery. So now the argument has not been show up. I also know that a lot of Chinese company, they put a lot of money in the graphene material for the for the lithium battery. Besides for the lithium battery, therefore also for other applications. So now people have already came up, but actually there's some new word is called carbon economy. Okay, carbon economy actually we don't know how far, but I do believe the carbon is a very useful materials, and then what's the market and what's the situation for the market we don't know now. A lot of company, even like the China very big company Huawei, they put a lot of the money to the graphene. They want to use the graphene to replace the silicon, okay, for the future, for the computer and also for the a lot of chips. So we don't know how far we go, but do remember that carbon-based material, especially for the graphene or the carbon nanotube, later on maybe diamond, they do have big application in our daily lives. They will affect our life. Actually, the technology advance is very important. I do believe everybody knows that actually when I was young, right, at that time, I have no TV, okay, and then when I was maybe 10 years old, okay, the house have the electricity, and then we have the electric bulb, right, and then the first time I look at the TV is a very small one, and white and black, right, and then maybe I was 15 years old, and then I go to my dad's actually the company, and then the first time I see actually the color TV, right? And then I do remember that actually at the time when I get married, and then I buy the very big TV. It's very heavy. Now you look at the TV, actually is now we have a where the TV show up actually is very flexible. So the technology we don't know. Now just like now people claim the carbon-based materials. Maybe 10 years later, maybe 5 years later, actually carbon-based material will replace a lot of things. Who knows? We don't know, right? But do remember that actually the technology actually is advanced, is very, very fast. And also I can give another example. When I was actually in the high school, the first time I touched the computer actually is Apple, okay. I know that actually the computer is Apple, but the language actually is C language, right? It's very slowly. And then when I become the graduate student in China, and then the computer is 286, 386, and then 486 at that time is very, very expensive. Actually, my boss told me that when he buys the 486, will cost about $10,000 US. is 92. That means 92. Is 95, 92, yeah, 92. Now you look at your computer, okay. It's much faster compared to previous the computer. So that's actually the technology advance. Now it's very hard to predict. Some new material came up. We don't know when this material will get into your life. But we do believe the time for the new material becomes application and then enter your life. This duration becomes shorter and shorter. Okay. So one thing actually now the carbon-based material is very important is shown here. Look at here because as I mentioned before, like the graphene, okay, in the layer, all this material actually is connect together is through the carbon-carbon bonding. Okay, so all this carbon-carbon bonding together. So this actually a piece of a material is very strong. So you can look at it here. Now I use a tool tracker to demonstrate that in the room temperature at the 20 degree, you can look at this strength is 2 to 3 gigapascal. Okay, so it's very, very strong. So that means if you try to break this carbon-carbon bonding, break this material, you want to use this strength 2 to 3 gigapascal. Okay, so this is the room temperature. More important things, this guy even in the high temperature, most of the material in high temperature, actually the property will decrease a lot. But for this guy, this material, even let's say 2000 degree, if you want to break this bonding and break this material, you still use the same strength. So that means this material in the room temperature, in the high temperature, is a very perfect material, right? Another things, in plan and then vertical plan. So if we all these materials stacked together, actually this pi stacking, this is very weak. So that means, for example, when you first time go to the primary school, you use the pencil. The pencil inside is graphene, okay? It's graphene-based materials. Not graphene, sorry, graphite-based materials. So that's why you can use the pencil, can write the words on the paper. Why something like that? Because all this layer will be fall down, so you can easy to write it. Otherwise, if the bonding is much stronger, you cannot use a pencil to write any word in paper. Okay, so that is the reason. So, and people, some research group get up this idea, and then they just use a pencil to write something in the paper, and then they can make this several layer graphene. Use this method, right? Previous actually why the people give the Nobel Prize to the England scientists. They use the graphite and then they use tape to peel off and then get a single layer of the graphene, and then they measure the field effect transistor, and then they claim this material is perfect material. And then 2005 they get a Nobel Prize. Oh, sorry, 2010. Okay. 2005, they reported the paper in the Science. 5 years. This is very fast, actually, to give the award the Nobel Prize. So later on, actually, he used the tape, and then some people said, why not use actually the pencil, just direct writing? This still can get actually several layer, the graphene. Okay. So this actually the implant. You can see this energy. Okay. Because this actually have very strong bonding. This energy is 516 kJ per mole, but the implant actually less than 10 kJ per mole. Okay, so that's actually the implant. So that's why we can use it actually to give the pressure. We can use it to write. Okay. So another thing actually is for the carbon material, the surface is something. This carbon-based material surface is very, very clean. This guy actually is not allowed this actually some small molecules stick on the surface. However, for the graphite, for the oxide or the GU, actually the graphene oxide, when oxidized, this guy can dissolve in the water. Why can dissolve in the water? Can deposit in the water? Because in the surface have a lot of wedge group. This wedge group is easy to form the bonding. So the GU can easy to stay in the water. Right? The same thing is here. Okay, the surface become very dirty, and then that means you have a very functionalized surface. If you functionalize the surface, obviously, and then some molecule can stay on the surface. So that's actually I don't know some you guys do the FYP in the Professor Zhang Hua's group. His group actually work on the carbon materials for all the carbon gels, for the water treatment and also for the oil treatment. So for the water treatment, actually in the surface, he functionalized with the hydrophobic materials. Hydrophilic materials. When hydrophilic materials, so now, for example, we have the water here. The water, you may have, we have the organic solvent here. Organic solvent inside maybe have some water. So in this case, normally how to remove the water? We use some, the dry agent to dry it. But use his material, because his material surface is very hydrophilic. So in this case, you put it to an organic solvent, you shake it, and the water can easily to absorbed by this actually the carbon gels can easily to remove this the water from the organic solvent. Or another things, if you do the functionalizer, become the hydrophobic. So in this case, in the water, if you have organic species in the water, and you can easily to remove the organic species. So that means it's a very useful material. Actually, 1 year ago, maybe 2 years ago, in the Singapore, actually the harbor, they have some oil leaking. Okay, for the oil leaking, they have seawater. If you have material, if you dumping the water, only absorb the oil, not absorb the water. So that's actually very useful, right? And also for a lot of the actually case, like for example in China, like some chemical actually fall down in the river, and then you use this material to absorb only the organic chemicals, and they have no effect to the water, and then that should be really, really useful. Okay, so this material is really depends how you do the functionalize the surface become super hydrophobic or super hydrophilic. They do have different applications, and also of course Professor Zhang Hua's group. I do believe he applies several of the pattern for this. Actually, yeah, it's a very nice material for applications. Okay, so another thing is actually normally, as I mentioned before, the clean surface, the water is not easy to stick on the carbon surface. Why something like that? Because carbon surface actually have a lot of the benzene ring. Okay, benzene ring actually is organic species. Actually is hydrophobic. So that means if you have water fall down on the surface, actually water is not stay on this surface, graphene surface. However, if your surface oxidize, like oxide actually have a lot of wedge group. The wedge group can easily form the hydrogen bonding with water. So in this case, water can easily to stay on the surface. Just like, for example, if you have the graphite, you oxidize, become GU, and the GU can soluble in water. Why something like that? Because GU can be from the hydrogen bonding with water, and then can easily to deposit in the water, become clear solution, right? Yes. Any question? No. Okay, if you do such as actually the graphene is a very nice material, because this one, beside actually to the lithium battery, beside for example to do the for the absorption, 3D graphene for the hydrophobic or hydrophilic. Besides that, actually this material is a very nice conducting materials. Later on, we are going to talk about actually in the nano-composite part. We are going to talk about it. This guy actually is very conducting. So of course, it's transparent. Now we use the conducting actually if we do the solid cell device fabrication in the some group, you maybe use ITU. ITU big problem is what? Indium. Indium price is very, very expensive. Now indium price is more than the gold. And also the amount for the indium in our ores is limited. So that means someday we'll use up. So in this case, we need to find some material to replace indium oxide. Probably carbon. Probably carbon is a very nice material. Okay. So that's why a lot of group to focus on this one, and then to make the graphene film which is flexible, which can replace actually the indium oxide or ITU indium tin oxide the system. Okay. Or another thing actually is for the chemical stability. Normally, For the tin oxide, indium tin oxide actually is not that chemical stable, especially for the strong acid or base. But for the graphene, they can be very stable, actually in the high range, right? So this actually is a very nice material, okay. So another thing is actually, this surface is actually easy to absorb the oxygen. Why something like that? Actually, we have a lot of the pi ring on the surface. Pi ring, they do have electron. Actually, in this case, this electron can have strong interaction with oxygen. So oxygen can stay on the surface. In this case, when oxygen stays on the surface, and then another oxygen cannot easy to get inside to oxidize. So that's another thing that will confirm that graphene or carbon-based material in the room temperature to the 400 degrees is pretty much stable. It's not that easy to oxidize. However, when here actually still is the same thing, because actually when oxygen stays on the surface, it's dynamic. Okay, oxygen can, for example, can easy to go, and then another oxygen get in to kick another oxygen out. That's in the room temperature. However, when temperature, okay, I should remove one slide to higher. When temperature become higher, what will happen? When temperature become higher, actually oxygen stay on the surface, and then this carbon active energy will become higher. Higher carbon will become more active. So in this case, oxygen meet with carbon will easy to react it when the temperature more than 400 degrees, and then this surface will be oxidized. Okay, and oxidized, and then carbon will become thin and thin. Okay. So carbon actually, graphite and carbon is anisotropic material. So this should be easy to understand. Actually, the previous we did talk about several, the factors. One is actually, for example, the heat. When you heat up in the middle, in the middle temperature can go to 1000 degrees. However, actually on the surface, the temperature is still 20 degrees, right? So this we have talk about. And also we talk about, for example, in plane, the heat transport actually is very high, but vertical plane actually heat transport connectivity is smaller, right? This we did talk about. And also we talk about, for example, in plane, if you try to break this bonding, normally the energy you want to use is 2 to 3 gigapascal. However, vertical plane, right, is very soft. Like carbon-based material is very soft, so that's why you can use a pencil, can writing on this paper, right? So this definitely tell us actually carbon-based material or graphene-based material is anisotropic. Okay. So another thing actually is the turbulence. This turbulence is tell us actually this really depends on how to actually make the preform, because later on when we make the carbon-based materials, it really depends on you use a carbon fiber to make the preform, and then this you can turbulence. Okay, so all this material actually this is like a breaker. This one have big application in airplane. So that's how I tell you guys. Them airplane tires they use this such things, right? This can easy to remove this heat, and when touchdown, and then generate a lot of heat, and this guy never become change shape. So this is very important. Okay. Now one thing is how to make this carbon-carbon composite, right? We talk about a lot of the properties. Now one thing is how to make it. Make it actually one thing we always start in preform. So for carbon composite, what do you make it? You should use a preform. We have no other way, right? So use a preform. Of course, the preform actually is from the carbon fiber. How to make the carbon fiber? Again, we need to use a spin. We're starting from polymer. How to do the spin? Like we have 4 spin method. We have 14, but in class we only require 4. We have melt spin, dry spin, wet spin, and the gel spin, right? And then when we spin, make the fiber, it's not enough. That's only for the polymer fiber. From polymer fiber to carbon fiber or to graphite fiber, we still another 4 steps. You can remember that. We need to stabilize, right, and then carbonization, and then graphitization, right? So this one you should don't know. You should go back to look at it. And then when we make this preform, and then what do we do? we need to actually the passing gas or the liquid precursor matrix inside. When we put it in, and then all this actually the gas or the liquid will fill in. Yours actually the empty part. When you fill in empty part, and then that's only the small molecular precursor. You need to heat up some certain temperature, and then the precursor will be decomposed, become carbon. That means you need to carbonization. During we do the carbonization, another problem will show up is all these organic precursors, when decomposed become carbon, they will lose a small molecule. When they lose a small molecule, and then they will introduce a hole inside. That hole or void, you need to go back to the field again, right? So typical actually in the procedure is here, okay. We have this carbon fiber platform, right? You have covered platform, of course you have two ways. This really depends on your precursor. Your precursor actually is a small molecule, easy to evaporate. You can use the CVD method or CVI method. That means use gas. If you carbon-based precursor actually is the molecule where it becomes larger, and then you can use the liquid method, right? Liquid method actually we just squeeze in. When you squeeze in, of course you need to carbonization, right? The temperature is about 500 to 1000 degrees. When you do the carbonization, actually you lose a small molecule. That means you have a lot of the hole inside. So this hole you need to go back to the fill again. So that means why I put the 1 to 5 times to fill the hole, right? Same thing here, right? And then during the composition, actually you still have hole inside. You need to do 1 to 3 times to fill in. After that, you get a carbon composite materials, and it's still not enough. You still need to go very high temperature to do crystallization, right? So that means in why you need to go to the 2800 degree. And this treatment should be in the inert gas. Normally we use argon, okay? Right? We use argon to treat it, and then you can get a carbon-carbon composite. So from here you look at it, actually carbon composite. Why carbon-carbon composite is very expensive? That you look at the procedure, you look at the temperature, right? So you can immediately see the carbon-carbon composite material is very, very expensive. Okay, so now carbon-carbon composite actually have big application is actually in the space, right? Because it's very light, it's very strong. But the big problem is what is when the temperature go more than 400 degrees, this guy is easy to oxidize. How to do protection? We have one method of 4 ways. The first things we need to use a silicon carbide or silicon nitride to protect it. And in tutorial question, actually, I have to tell you guys, whatever for the silicon carbide actually is a very fragile. So that means that during processing, you may be form a lot of crack on the surface. This crack actually later on is a big problem. The oxygen can easy to get inside. So what do? We need to use actually the oxide inhibitor. Oxide inhibitor actually this concept is borrowed from the stainless steel. So that means you put some active element before oxygen react with the carbon, and then active element will react oxygen first. Normally, typical we have the titanium or germanium, like composite, and that one actually can actually oxygen inhibit. Even in this case, it's not enough. So we are go to the third step. We use the glass sealant. So what do you mean glass sealant? Glass sealant, so that means you have organic small molecules you put inside, because this material hit at some certain temperature, this guy will become liquid. And then you have this crack here, and the liquid can easy to find this crack and fill in. And when this liquid to meet oxygen, and this guy will be oxidized from silicon oxide. Silicon oxide can easy to fill to become solidified, and then stop the oxygen to get inside, right? And after that, we also go to the last step. We still use the silicon carbide or silicon nitride to do packaging, right? But for here, I missed the one step actually is for the oxygen inhibit. Okay, so the correct answer you should follow the tutorial question. Okay, one method, 4 steps. Okay, of course, this guy has a lot of applications, right? For example, we can use this for the airplane, the car tires, right? And also, because this guy has a lot of high-way thermal conductivity, they do have a lot of applications, normally in some the high-tech applications. Okay, so that's all for today's actually the lecture. We still have time, so if you have any question, you can stay here, we can discuss. If you have no question, you can leave. Okay, this is one thing. Another thing, next week is the research week. Okay, so you guys just enjoy your research week. After research week, 1 week after research week, okay, we will have CA1. Okay, so see you the 1 week later. Okay, so starting from next week, we are going to talk about the functional composite. So that means we talk about the nanocomposite, and also we talk about the biocomposite, and also we talk about this application. Previously, we talk about thermoelectric applications. I have taken that part away. We just only talk about solar cell. Okay, so it should be enough for us. Okay, so if you have no question, you can leave. If you have any question, you can stay here. We can discuss. Okay.